Thank you. Thanks everyone for joining us today. So great to see all of you here and those who are joining in the live stream. You're here today because you want to learn how to use AWS HealthImaging to architect solutions to store and manage healthcare imaging data, but also power clinical research and machine learning use cases. My name is Zahn Iftikhar. I'm a healthcare solutions architect at AWS. And today I'll also be joined by Linta, my colleague, to share her insights into how customers are exploring imaging workloads on AWS. Today, with the help of a virtual whiteboard, we'll go over event-driven data flows and architectures that support them. Let's go on to the whiteboard. All right. For any of you who work in the health imaging space, it would come as no surprise to you when I say health imaging has a massive data problem. Just to put that into context, over 30% of the world's data is produced from healthcare. And 90% of that is from healthcare imaging. What contributes to that is over 3.6 billion imaging procedures that take place every year. On an average, at this moment, an imaging study is somewhere around 150 megabytes in size. But that's where we are today. With digital pathology on the horizon, that's expected to explode with over 10 times as much. So not only do we have a challenge with managing data today, it's something that's expected to become even more of a challenge as we move forward. Now, customers have been asking AWS how we can help them solve the ever-growing storage requirements for their imaging workloads. Just by migrating imaging repositories and workloads to cloud, you can solve a lot of the challenges, especially when it comes to scale. Just to give you an example, a healthcare executive told me that just by migrating their imaging repository to cloud, they've been able to do away with the pain of continuously procuring more and more storage every couple of months. So just the scale that it provides solves for a lot. But that doesn't solve for everything. Customers still have to manage a plethora of storage services and interfaces like DICOM that they need to produce on top. And to address these challenges, AWS launched AWS HealthImaging. HealthImaging is a service that makes it easy to store, manage, and share imaging data at petabyte scale. It ingests data in DICOM P10 format and provides purpose-built storage and low latency cloud-native APIs for access of that data. There's a few advantages and benefits that health imaging provides to customers. The first one is around reduction in TCO, or total cost of ownership. Health imaging can help reduce cost of storing imaging data by up to 40%. And there's a few ways it does that. One is using advanced compression technology to compress images as they're stored. The second one is intelligent tiering across frequently accessed and archival tiers of data. So depending on how frequently data is accessed, it can be archived onto lower cost tiers to manage the cost. And thirdly is removing duplication. Duplication of data in the imaging space is a problem, is a challenge. For example, if you take a 1 GB CAT scan, you'd expect it to be available in the imaging device. You'd have it in your PACS, your VNA, your radiology packs, your cardiology packs, your disaster recovery system, and other specialty systems. Not only does that provide challenges in terms of the cost, but also keeping all these systems in synchronization is a problem. The way health imaging addresses that is providing you a capability to have a single source of your imaging data in the cloud and access it across multiple systems and workloads without having impact to each other. So you can have a single source of your data, have it accessible at low latency across your ecosystem of services. Now, cost is not the only considerations. Our customers tell us that they want to be able to deliver images back to their clinicians and their users at high speed. So speed is obviously important. Health imaging enables subsecond retrieval of imaging from anywhere with using cloud-native APIs. And it does that with a combination of that compression algorithm we talked about. So the compression doesn't help just with storage, but also transmission of this data, combined with AWS's global network infrastructure for low latency, high speed network infrastructure. And being a managed service, it helps you also manage the overhead of managing infrastructure and reduces that overall. So these are some of the key benefits customers are realizing with health imaging. Now that you have an understanding of health imaging, let's take a look at a few use cases. So on the screen here, you have your traditional imaging facility, your hospital network, where you'd have a PACS or a VNA or an imaging device. Imagine that you're a builder for an organization that's looking to onboard to health imaging, and you're tasked with providing an architecture to support ingestion of data and also then downstream use of that data. So we'll look at a few use cases there. The first one is being able to ingest data at scale into AWS Health Imaging. And we'll look at that in more detail. Once the data comes in, you want to be able to provide fine-grained access control to your users and roles within your organization or outside to that data. So access control and fine-grained access control is imperative. That'll be our second use case. Your organization also wants to look at enabling machine learning capability to enhance clinical and imaging workflows within your organization. So we're going to look at how machine learning capability can be included within your imaging workflows. So that's our third use case. And lastly, you want to be able to, after processing the data through your imaging workflows, you want to be able to provide this back to your clinicians at low latency. So we'll look at how we provide this data back to your clinicians for our fourth use case. Let's start with the first one. We'll dive a little bit deeper into the architecture now. With health imaging, to start that ingestion process, you start by bringing your data into an S3 staging bucket. For those of you who may not have heard of S3, S3 is Amazon's highly scalable simple storage service, or an object store. It supports a number of native and third-party solutions to help you bring data in. So for example, if you wanted to do an initial load of data into health imaging, you could bring it in using a service like AWS Data Sync or a partner solution. So that would be a one-time sync into S3, which can then make an API call to health imaging to ingest that data in. But that's not your only problem. You need to be able to synchronize data as it's produced at the source and bring it into health imaging in near real time. For that purpose, we can make use of edge compute devices in the hospital or imaging facility. This can be a server running something like AWS IoT Greengrass to listen in from your imaging services and then push that data into Amazon S3. Once the data is in S3, we can use the power of event-driven architectures to continuously push that into health imaging. For this purpose, we'll introduce a couple of new services. So one is SQS, and the other is AWS Lambda. SQS is a simple queuing service. It's a managed message queue that is built for distributed and scalable serverless applications. And Lambda lets you run your code without having to manage infrastructure and servers. The way they come together to support this use case is S3 allows you to trigger messages into SQS. So as images are loaded into S3, you can publish a message here, which can then be consumed by a Lambda function to push this data into health imaging via API calls. This is a cleaner version of what this looks like, and we've introduced a metadata and workflow database here. Again, you have choice of what you want to use here, but you might want to manage your workflows using this capability. A couple of things to highlight. So what we've used here is what we call a serverless architecture. And there's two key benefits that it provides you. One is scalability. Each workflow within this architecture can be duplicated over and over again, which means that you can scale this to ingest thousands and thousands of images in parallel. So the scalability is really key. And the other piece is the modular nature of this architecture. It's extensible. So for example, this is a simple workflow where we're ingesting data into the imaging service, but you can break this here. And you can introduce more modules. For example, you may want to do, as data comes in, you may want to do DICOM metadata validation, or you may want to do malware scanning, and you can easily extend this architecture to do so. Now, as health imaging ingests data from the S3 bucket, it optimizes it for storage and delivery. And there's a couple of key things it does with this data. The first one is encoding that data using a codec called high throughput JPEG 2000. This is a lossless codec that allows you to compress that data automatically, but also improve the efficiency both from storage and for delivery purposes. And another key concept is that of image sets. Image set is a construct within health imaging. And it's a way to optimize storage for related imaging studies. And we'll look at that in a little bit more detail as well. So if we dive into the data model within health imaging, now that we've imported our data, at the top you've got the data store. Your data store is essentially the logical separation of your data that you bring into health imaging. This data is replicated across 3 availability zones within an AWS region for resiliency. That data is stored in the form of image sets. If you understand DICOM, image sets are essentially matching SOP instances within a DICOM series that are optimized and stored together. So essentially, an image set may have one or more images within. The other key thing health imaging does is it splits out the metadata in image frames, or the image pixels. That becomes really powerful, because what you can do now is you've got access to APIs that allow you to access each of them separately. So you can search through, you can update metadata without having to touch the image or download the whole image in itself. That provides efficiency in your workflows. Okay. So what we've been able to achieve so far is bring data at scale into health imaging. Our second use case is that you need to be able to provide fine-grained access control to multiple users within your organization to that data, which has potential sensitive information and patient information. Here, we can make use of what we call resource tags. Essentially, each image set can be tagged by a user-defined key-value pair that allow you to then use those key-value pairs or those tags in your access policies. So in this example, if we have 3 image sets, we can have a tag called patient information, or PI. And you can set that value to true or false. So it may be false for a couple of those images, while true for one. In your use case, you have 2 personas. One is that of a clinician, and one is that of a researcher. Now that we understand, and now that we've tagged our images, and also we understand who we need to provide access to, we can start to author our access policies. So for the clinician role, we can simply author a user policy that says that role can access all images, because you're not worried about restricting it to only non-patient information. But the researcher, we can now have an access policy which says that it can only access image sets where the patient information flag is false. What this will then essentially translate back down to is your clinician will be able to access all data, but for the researcher, they'll be able to make API calls to access these 2 image sets, but when they try to access an image set where the tag is true, that access would simply be denied. So now you have the ability to manage access to your imaging data. So we've got the basics done. Let's look at our third use case now, which is that of machine learning. Now, often when customers are looking to build machine learning models for imaging data sets, there's an inherent requirement to anonymize data before you send it for training. If you recall, we looked at the API, the metadata APIs that health imaging provides you, which means for you is that, what that means for you is that you can author a simple Lambda function and make API calls to your image sets to anonymize the metadata and remove patient information. One real key thing here is metadata is versioned within health imaging. What that means is all history is preserved. So you can anonymize metadata, but you can continue to access previous versions of that metadata if you need to. Now, to start our machine learning process, often customers would start with a machine learning platform like Amazon SageMaker. Amazon SageMaker is a managed service and a tool set for machine learning that helps you build, train, and deploy machine learning models at scale. It manages the infrastructure that's required to do all of that. Customers would often start with SageMaker to pre-process that data before you start to train your model. Pre-processing can be things like image segmentation or extracting radiomics features from that data. Radiomics features essentially allow you to provide a quantitative view of that image. So essentially translating pixels to numericals, which can then be used in a machine learning model. Those radiomics features can be stored within SageMaker in a capability called feature store. And once you have once your data is pre-processed, you've extracted the features, you can then you can use SageMaker to then train your machine learning model. That brings in your data as well as the radiomics features. Again, this is extensible. You can also start to combine imaging data with genomics and clinical data. So we can bring in, for example, omics data or clinical or patient history. And this can be combined together to create what we'd call a multimodal machine learning model to bring it all together. Again, a cleaner view of what this looks like. Now, examples of how customers are using machine learning on imaging data are things like image quality control. So you want to, as you ingest data in, you want to do quality control to check the viability of that data for downstream processing or viewing. Other examples are image segmentation. These are used in use cases like stroke imaging. So if you have a stroke, MRI, or CT scan, you can use machine learning to segment and calculate the volume of a hemorrhage, which can then be used to support clinical decision downstream on prognosis for the patient. Or, as we discussed earlier, you can use multimodal analysis. So you can look at combining a patient's image with their clinical history and their genomic makeup to provide precision medicine use cases. Once you've trained the data, the model in SageMaker, with a click of a few buttons or an API call, you can now deploy this model within SageMaker for inference and start to make use of it within your workflows. So, we've now got our data in health imaging, and we've got our trained model. How do we then start to bring the output of that model back into our imaging repository? And we'll make use of our trusted serverless services, SQS and Lambda. Similar to before, as an object or an image is uploaded into health imaging, you can trigger a message to SQS, which Lambda can be listening to, which can then push that to your SageMaker machine learning model. The output of that can then be fed back into health imaging. So think, for example, if you have an overlay over your image, which provides the machine learning output, you can push this back into health imaging for viewing downstream. So what we've looked at so far is how do you ingest data at scale into health imaging? How do you provide access control to that data, or on top of that data? And then how do you enable machine learning capability with that data? With this, I'd like to invite Linda, my colleague, to talk you through how she's working with customers to build prototypes to enhance the fourth use case, which is the delivery of that data back to clinicians at low latency.
Thank you, On. Hello, everyone. I hope you all are enjoying the AWS Health Imaging session, and you have a good understanding of the capabilities of health imaging and the use cases. Now, I will show you how AWS Health Imaging and AWS Global Network can address several customer problems in a teleradiology business.
Linda, I might get you to start off by defining for us what is teleradiology and what challenges it presents to customers in a traditional environment.
Sure, On. So, teleradiology is the transmission of medical images taken in procedures like X-rays, CT scan, MRI from one location to another for the purpose of sharing it with radiologists. Now, what you're seeing on screen is a typical teleradiology setup. So, for example, if you have a medical imaging facility in Australia, patients will be going and visiting this facility to take their medical images. Now, what teleradiology allows is, it allows the radiologists to provide their services to these patients in Australia without having to be physically present in Australia. So they can be in Asia Pacific, they can be in Europe, they can be in Africa or anywhere in the world. Now, where this becomes particularly important is if there is a requirement for specialist radiologists like an MRI radiologist or a pediatric radiologist. Clinics and hospitals don't always have ready access to these specialist radiologists. So teleradiology also helps to leverage the international time zones and provide 24/7 service, at the same time making sure that the radiologists only ever work during daylight hours. Now let's have a look at the problem spaces that teleradiology business is facing. So the medical images that we are talking about, these images are high resolution images because for the need for detailed and accurate visualization of the anatomical structures and abnormalities. The images are also large in size, ranging from megabytes to a few gigabytes. Now, radiologists use an application called Image Viewer to view these images. The requirement of a radiologist is, using this viewer, they should be able to retrieve, view, and read these images with high accuracy and high performance from anywhere in the world in near real time. What that means is that the distribution of the images across the globe have to be highly performant and low latency.
Great, thanks, Linda. And I guess the obvious question, how does health imaging solve for that challenge?
Sure. So with AWS Health Imaging, customers can store their medical images in the health imaging data store and establish the performance they need to distribute the images across the globe, right? So they can be across the globe, across intercontinental distance, such as between Australia, Asia Pacific, Africa, and Europe. Customers can also leverage AWS Global Network and Content Delivery Network to further accelerate the image delivery. Now, I will take you through the architecture of a prototype that we have developed to evaluate the performance of health imaging, image delivery across intercontinental distance from AHI data store, from health imaging data store to an intercontinentally distant viewer. So in this prototype, we used OHIV viewer. So OHIV stands for Open Health Imaging Foundation. It is an open source viewer. So in this architecture, we deployed this as a static website in an S3 bucket. We placed this static website behind CloudFront, Amazon's content delivery network. We placed the static website as well as Amazon Health Imaging behind the content delivery network. This is to accelerate the delivery of the image when a radiologist tries to access the image through the content delivery network, right? So when a radiologist tries to access the image, the flow will go through web application firewall. which is a service that protects the CloudFront distribution from malicious attack. So what WAF does is, it filters all the incoming traffic, it applies rules granting and denying access based on who is making the call. So this is how the flow goes. Now, one of the other key features that we built is CloudFront Cache. So when a radiologist tries to access the image for the first time, the image will be retrieved from the HealthImaging data store, where the image is stored. And it will also be stored in the CloudFront cache at a location which is nearest to the radiologist. So what happens is, if you try to access the image for a second time, it will be retrieved from the CloudFront cache, making the whole distribution much faster. We have also used Cognito. This is for user management and authenticating the users in an OpenID Connect compatible manner. The whole architecture was deployed in the Sydney region. Now, one of the key goals of HealthImaging when we released it was to achieve subsecond time to load the first image in an imaging study. So as part of testing this prototype, we loaded a CT scan, which is a fairly large image, loaded in Sydney from US Minneapolis in 600 milliseconds. Now, this is a much pretty picture of the whole architecture.
Thanks, Linda. You also mentioned the OHIV, which is an open source tool set. Is there a particular reason for using that, and what would you recommend to customers who want to run a production image viewer?
Sure, good question. So we used OHIV Viewer because, as I mentioned, it is an open source viewer, and it gave us the flexibility to make the changes that was required to meet the requirements of the prototype. OHIV Viewer also gives you the code to deploy it as a static website. It also provides extensible APIs which will support dynamic behaviors like retrieval of the images. Now, one of the limitations of OHIV Viewer is the worklist of OHIV Viewer doesn't support prefetching of images. This limitation happens if your use case have very large images and low bandwidth. So there are customer use cases where the image sizes are up to 5 GB. So if you have 5 GB of data, big images with 5 GB of data, it is difficult to stream 5 GB of data on demand from HealthImaging data store to a client-side rendering viewer like OHIV. The main limitation in this case is the internet bandwidth. So for example, if you have a 1 Gbps connection, and if you have 5 GB of data, to stream 5 GB of data, it will take 40 seconds. So our recommendation is, if your use case have very large studies, what we recommend is do prefetching if you want to use a client-side rendering viewer like OHIV, and if you have, specifically if you have a low bandwidth issue. But if your use case doesn't have very large studies, which is GBs, the architecture works perfectly well.
Awesome. Thank you so much, Linda. Right. Go back to the slides, please. All right. So we looked at a few use cases today in terms of how you can start to leverage health imaging to build clinical workflows and imaging workflows. There's a lot more that customers are able to do. So we have customers today looking at using health imaging to support enterprise imaging requirements, building packs, and other imaging capability. We have customers looking at long-term archival to reduce the ever-growing cost and scale required for imaging on premises. We looked at machine learning capability. There's a lot that opens up in cloud as well. Once your data is in the cloud, you can do a lot more with machine learning. So customers are able to scan their whole imaging repositories at a patient cohort level, something that would have taken months or years on premises, and something they can do within days or hours in the cloud. And multimodal analysis is something that's coming up more and more. Customers are wanting to provide that very specific view of the patient. It's not just about, it's just the image in isolation. You want to be able to provide it with clinical history. You want to be able to combine it with the genomic makeup of that individual as well. All right. We'd like to leave you with a few resources to get you started. So the first QR code here is a link to code repository, which has some sample code, which includes some of the architectures we looked at today to get you start building. And the second one is a blog post that dives deep into how to integrate SageMaker, which is the machine learning platform, with health imaging for machine learning use cases as well. And if you're looking to learn more about AWS, AWS Skills Builder is a great resource. You have access to digital trainings, hands-on labs, role-based games to help you learn, but also then validate your skills using AWS certifications as well. And that's about it. Thank you so much for joining us.
Thank you.
And I will go to the last one. Yep. If you haven't had a chance to do it, please use the QR code to download the app. And please provide us feedback. We really appreciate it. Helps us know what went well and how we can improve in the future. Thank you.
Thank you, everyone.
Thank you.
Thank you.